Hi, we're here to review techniques of integration, and as I was preparing for this video and this problem set, I realized most of techniques of integration comes down to use substitution of various flavors. Not all, but a lot. So if you would like to give yourself a bit of a challenge, perhaps, you could pause this video already and just run through this set of problems, see what you can figure out. You can see on my screen, I'm already giving you a couple of hints for two of the questions that are not partial, or that are not use substitution. So you can see what I'm going to do. But for a lot of the rest, you might want to choose to just try the problems yourself. Okay, welcome back from trying the problems yourself. So the first question is partial fractions. And the reason that I would be using partial fractions to find this antiderivative is because I can see observationally that that denominator is something that we know how to factor. So I know that this integral is going to be equivalent to just factoring this bottom. And that tells me that I can use partial fractions to decompose. So I would have this same expression, that is my integrand, equal to the sum of two different fractions. And so essentially this is like saying, okay, I know I could add fractions to get that because it would have a common denominator and this would be the common denominator. It's just undoing that process. If you recall, we will multiply through by x plus 5, x minus 1 in this case. That would leave me with the 1 from the numerator here. It would leave me with the a from the numerator multiplied by x minus 1 and the b from that numerator multiplied by x plus 5. Again, the logic of this, because I think some of you maybe just do it without knowing why, we're multiplying everything in the equation by that quantity, but not in a denominator, up in a top, right, in the numerator. All right, then our technique would have us set x equal to -5 and x equal to 1, because that's what makes each of these in turn negative or equal to 0. And that's going to leave us with a is -1/6 and b is +1/6. I glossed over some of that arithmetic. Please do check it yourself. You never know, I might have made a mistake. That would be bad. Okay, so now if I put in 1/6 where b is in this statement, I'd have 1/6 over x minus 1. So notice I am returning now to my original problem. Right, taking this -1/6, putting it in as the numerator on x plus 5. So now this is my integrand. I could just handle it now, right? Because it's going to be 1/6 is just a multiplier. I could pull that out mentally, and then I just have a natural log. So I've got 1/6 natural log absolute value, and same on this part. And then plus my constant of integration. Okay. The next bit is one that we're going to do with splitting. Okay. I look at this at first and I really would like it to be a u substitution, right? Where this u might be the denominator, but I can see I'd get 2x and I just have an x on top. I also have an extra 2. So that's problematic, but maybe I can utilize my idea if I split this up. So it's like having these two fractions added together. So now think about, I haven't written everything, but think about if you were adding these two fractions together, how you'd have a common denominator and you'd add the tops. We're just undoing that, right? The opposite is also true mathematically. Okay, so those are my two integrals. And then on this left-hand integral, if I were to just insert and balance, I now would have that natural log situation that I was thinking about. And I think if I take out this 2, I recognize one of my favorite integrals of all time, hopefully yours as well. Okay, so over here, I'd have 1/2. This is my u. This is du. I think that's straightforward enough that we don't fully have to write out the u substitution, but if you personally need to write out the u substitution, please do. Over here, this is arctan, so the 2 is going to come down. I'd have 1/2 from this part, right? I have x squared plus 2 squared, So I'd have 1 over 2 as my part of my arctan antiderivative. And my argument here would be x over 2. And that's the story, okay? Number 3. On this one, I am noting that a is a constant. And I am noting that this looks like maybe it would be a convenient u substitution, right? If I take the derivative of natural log of x, I get 1 over x, and I have a 1 over x kind of hanging out here. So I believe this will work great if we just pull that a out and then let u equal a plus natural log of x, the part that's inside the radical. And then the derivative of a is 0, and the derivative of natural log of x is, as I just mentioned, 1 over x. So if I apply this u substitution cloud, I think we're good to go, because now my integral is just the a on the front. I've got 1 over x dx, so those parts, this and this, right, all of that is my du. And then I have a u with a radical on the bottom. Okay, so this is really just a times u to the negative 1/2 du. And that is just power rule. So I have I have a 2, I have a square root of u. Whoop, that pen. Sometimes if I'm a little slow, it misinterprets me. That, and then plus c, and so then I would put that u back in, and my answer choice is right here. I guess I could, is there anything in here that I didn't say? No, I don't think so. That's a little neater than what I just did, but no cloud. Really should have a cloud. All right. Here's number 4. Number 4 is a little spicy in that you just have to basically not panic. That is so often my advice, but is actually also true. Looking at that, it's definitely testing me something about u substitution because I'm integrating functions inside of functions, right? That's calling out u substitution. But it's doing it symbolically, right? The only function we actually have is 1/2 of x. The other functions that are mentioned, the f and the g, are written symbolically. So I just have to, like I said, stay calm. Don't panic, okay? So let's just like with other u substitution, like the u substitution we just did, we let the innermost function be our u. That's generally true, okay? So let's just see if it's true here. So let's let u equal g. I don't like that x over 2. I'm going to write it as 1/2 x. I don't know. I think I'd forget to take the derivative properly. And then du, if I am taking a derivative of a function inside of a function, that uses chain rule. Derivative of the outside, keep the inside, times derivative of the inside. Okay. Am I feeling any better about this? I think I am if I put in a 1/2. So this 1/2 is trying to match that, balance that. And now I think I'm in pretty good shape because g prime 1/2 x, all of this is right here. That's du, okay? So really what I have is 2 integral of f prime of u du, and that is not hard, okay? So this is just 2 f of my substitution cloud plus c, and then I'm going to put this back in, and that, my friends, is option B. Yeah, cool. Stay calm. Stay calm. Your brain can't work if you're panicking, so no panicking, okay? Got to give yourself a little pep talk. I'm not kidding. Give yourself a little pep talk of, I've taken this whole class. I know things, right? Give yourself that talk, because if you're panic talking, your brain shuts down. That's just a fact, okay? So give yourself thought, a talk about how everything that you need is on the page and you are smart. It's facts. Okay, number 5. This is a u substitution question again, but it's one that is a definite integral. So notice that these bounds are x values right now. If I change my integral to be in terms of u, I either have to have placeholders there for a bit and then switch back to x, or I could just change to u-bounds. And looking at the fact that this question is asking for something that it's equivalent to, and it's not, all these answer choices still have integrals. They clearly are just trying to see if I understand the idea of u-bounds. So this is actually not that bad. Now that you've recognized all those things, you smart person, you. Okay, here's my cloud. That has to be what it is, okay? So that means that I need to insert a -4 and a -1/4. Okay, I'm kind of thinking these are going to be out. Okay, I'm not sure if that negative is going to somehow go away, but I don't think so. Maybe it is. I don't know. We'll see. Okay, so we've got all that going on, and then we're going to do our bounds. Okay, so if x were 1, what would u be? If I put in a 1 for x, I'd get 16. And if I put in a 3 for x, 20 minus 4 times 3, so 20 minus 12 is 8. Okay, I'm getting 8 and 16. So my understanding of that would be I'd have -1/4. Where there was a 1, I'd put a 16. Where there was an 8, or there was a 3, I'm going to put an 8. Oh, I see where the negative goes now. That was confusing and tricky, okay? So I really want this to be an answer choice, but it's not. The closest I have is choice A. Why is choice A the same? Because they flipped the bounds. And in flipping the bounds, they would flip that sign. So A is it. Woo! Smart. Staying calm. All right, and as our reward, we get a calculator question. That was very tongue-in-cheek, you guys. I hate the calculator questions. All right, but we just got to get through it, right? Okay, so this is clearly a fundamental theorem of calculus question because they're talking about an antiderivative, and they're giving me a value on the antiderivative and asking me to find a different one. So this is like first fundamental theorem or like poetic version. You might start this question by saying, okay, if I were to integrate the given, right? First fundamental theorem would say you do the antiderivative at the top bound minus the antiderivative at the bottom bound, and that's what this is going to equal, okay? So we can just reorganize this, right, with the things that we know. We know that f at pi is e, okay? And then f of 0 is what we're looking for. And this is something that we could find on our calculator, okay? Get from calculator. This is not how you'd show your work on an FRQ, but it's in multiple choice, so write it however you want. Okay, so I'm going to take e minus what I get from fn int, and that's going to tell me my answer. Okay, so e minus the fn int value from this part is going to give me f of 0, and that was just that. Okay, the fn int part, in case you wanted to know, this part that you get from your calculator is about 0.4285407, blah. Okay, make sure you're in radian mode. We're always in radian mode in our class. It's just physics. Oh, physics. Oh, physics. Why do you love the degree? This is a question I have. I mean, really. It's a rather arbitrary measure to divide something into 360 parts. I'm just saying. Okay, our next question is going to be a beautiful U substitution, shocking no one, okay? This is a situation where we're, again, staying calm, because if you look at that integrand, it's like, oh my gosh, what's happening? But then you remember arctan. Let's let that exponent be our U. Remember that that's just another way to write arctan. Don't panic, okay? And so 2 is going to ride along. The derivative of arctan is that guy. And then look, oh, it's right there in the problem. So all I need to do with my beautiful U substitution cloud is to insert a 2 and balance it with a 1/2. And now look at what we've got. We've got e to the u. All of that is du. Ah! Aren't you glad I don't sing more? That was pretty bad. Okay. And then we have bounds that are x's. So we're going to do a little thinking about our u bounds. Okay? So 2 arctan of 1 for the top bound. The angle whose tangent is 1 is pi over 4. So my top bound is going to be pi over 2. And 2, the angle whose tangent is 0, because 0 was the other bound. The angle whose tangent is 0 is the angle 0 radians. So that's going to stay a 0. Okay, now I have no need to go back into X world, okay, because I changed all of my components. So antiderive, put in my bounds, e to the 0 is 1, and that's this guy. Woo! All right. Number 8 comes down to knowing a definition. If I remember from the recording I made yesterday, I believe we had this definition in a problem in the last video too. So average value, 1 over b minus a, because that's my interval. And then integrate from a to b of my function. Ugh, what in the heck is this? Well, just plow ahead, friends, and keep telling yourself you are smart enough to do this. Okay, sine e to the cosine. Okay, and I left some space because I think I would really rather split this up because of how I'm going to think about that integrand. Okay, so it's really just 1 over b minus a integral of the whole thing, but I split it up because I want to do like different u substitution thinking. Okay, so if u is sine, the derivative of sine is cosine. So that's already an e to the u. So I could just make that e to the u with my bounds like that. Okay. While I'm in the neighborhood, let's think about this stupid fraction inside of a fraction situation. I've got 1 over pi over 2, so that's 2 over pi. Okay, and then over here, this is a place you could easily make a plus minus kind of sign error if you're me. The derivative of cosine is negative sine, so we need a negative, balance it with a negative. So over here, I'd have I'm going to write it as plus and negative. I think I'd make fewer mistakes that way. E to the cosine of x once I do my u substitution. And then pi over 2 and 0. Okay? Then we're going to plug stuff in. And it should all be pretty. Okay, let's find out. So 2 over pi. I'd have e to the, oh, now I have to do trig values. Okay, so e to the sine of pi over 2 minus e to the sine of 0. And then here I'd have subtraction from here. E to the cosine pi over 2 minus a negative, so plus e to the cosine at 0 is 1. Holy smokes. Okay, so then these two add together. These are both 1. Okay, so I've got 2 over pi, 2e minus 2. Which guy is that? That's this one. All right. Woo! That was a bit of a workout. Straightforward seeming problem that seems a little bit evil now that we take a look. We're almost done, folks, okay? All right. Especially if you're just fast forwarding to check your work. This is a lot less time consuming. Okay, let's look at 9. This is integration by parts, okay? You might recognize that because to set up finding the area of region R, you're just going to have this integral. And having a product, especially a product that contains natural log, is such a signal. I'm just saying, okay? So because I have bounds, I'm going to do a little side problem where I don't need to worry about the fact that I have bounds. Bounds wig me out in integration by parts. So I've got natural log 1 over x dx. My other part would be the 2x, which means this is x squared. So there is my box, and that tells me that my antiderivative would be u times v. Why did I write that? Oh, I guess I just was trying to think about the order there. So u times v minus the integral of v du. And so this x would cancel one of those x's. So my full antiderivative would just be this. Okay, I'm going to bring that into the main problem now. Okay, so here I'd have x squared ln of x minus x squared over 2, no c because I have bounds. Okay, and when you go through plugging in the bounds, you get a. I'm just going to skip that part, okay? Plug in an e, plug in a 1, do your math. All right, 10. We need to talk about 10. 10 is also a partial fraction problem, but sometimes y'all don't recognize that because of having the 4x plus 2. Somehow we have this misconception, maybe it's my fault, that you can only do partial fractions if you have a constant on the other, like in the numerator of the original, and that is just not the case, okay? So you still do the same exact process that we did on problem 1. Same exact process. Okay, so just to save a little bit of video time here, I'm watching that counter and it's just going up, up, up. Okay, I'm just going to show you this one. Okay, so you start where I have the word start. And you have your same old setup for partial fractions. Integrand equals fraction plus fraction with the separate factors. Multiply through, in this case, by x plus 3, x plus 1. Boom. Plug in -1, plug in -3 as 2 separate problems. Boom. And you should have the -1 and the positive 5. Put those in and you're done. It's the same process as number 1. So the whole reason for including this question is to point out to y'all that just because this has an x in the original problem, that doesn't take it out of partial fraction category, right? The fact that this is factorable on the bottom makes it say, maybe partial fractions would work here, okay? Number 11, improper integrals, okay, which which are the skills that we need for doing integral test eventually, among other things, okay? So here we want to think about what makes each of them improper. 1 and 3 are very clearly improper. 2 is the more obscured kind of improper, but that's improper because the domain of the integrand doesn't include 0. So we would be rewriting each of these as a limit. Now, given that it's multiple choice, I don't need to worry a ton about my format. I would have a limit as b goes to infinity, and this part would be b, and then I'd antiderive. Okay, at some point you get to this, and it's the limit as b approaches infinity. Okay, number 2 is the same integrand, so I'd have the same antiderivative. We would have rewritten it so the bottom bound a was a limit as a approaches 0 from the right, and this would be my antiderivative. Okay, so I'd be evaluating that limit. And then in the last one, this is a different integrand. So this is integrating x to the -3/2. And so I'd have x to the -1/2 as my antiderivative. I would have rewritten the top bound, right? This would be b approaching infinity. So I'd have a limit here, b approaches infinity. Okay, so we want to think about each of these limits in turn and which ones actually converge versus going to infinity. And the answer to that is shown right here. Okay, thanks for hanging in there through a long video. I hope this helped you review your techniques of integration. You could look at the packet from this unit, which was at the start of semester 2.